at the end, and then I go for a loop, and then, okay. I know the problem is that it's not so. I think that's right. I don't remember. So, recall. Thank you. As we said too, he's mad he did it. I'm about this much short. But other than that, CD project. More.
And Josh sent you guys email yesterday, the TA, about, I think he did a Zoom session last night if you needed help. Did it? Everyone get an email about that?
Negative.
You did not? Okay, I don't know who he emailed or where he got his email list from. He's in quarantine, so.
Yeah.
Okay. Yeah, if you have questions. Actually, I'm not, I don't think I'm supposed to say who's in quarantine, who's not. He is not available for 14 days or something.
What do you call it? It's color. I just gotta do the same thing. It's called red, but you might call it different. Based on how you see it. I'd say one thing. You can just wow. How would it look like? Yes. One lab should be said not lab and then sure. Right. I've been planning to do so yeah, I gotta do all
Okay, homework 8 link, the submission link is up there. I gave you until 5 o'clock to submit today's homework. I forgot to create the link, so. Okay. Let's see if the updated. Should be updating momentarily.
Surprising.
Haven't updated it for today yet. A little slow. A lot of people are hitting the site.
So we give you guys any word on the plan?
About what?
Like what's their?
I haven't heard a thing, so nothing at all. So I probably depends on what the numbers are doing. I'm hoping it levels off.
So what happens when we go? Locked down?
I think it would just be like we were probably. I'm hoping if we do go online in 2 weeks and then we'll return. But I have no idea. And it'll. What I plan to do would be continue like we did after spring break last year. So what I did was just asynchronous lectures, just upload the lectures to YouTube, and then give you assignments. But hopefully we won't do that. So we'll see. I did. So I had a few questions about some people struggling with the switch and detecting. So the project is, and this is on the website under today's lecture. Okay. This is just for switch 1. The code for the other switch would be identical. So just change the function name and the switch 1. But so what this is supposed to do is return 1 or true when the switch is pressed for the first time. So you could do this with like a state table. And any other time it's supposed to return false. Okay? You could modify it so it returns true when it's released, or true when it's held down. Okay, but in this project, you want it to return true only when it's first pressed and false at any other time. So if you've already done this, great. Stick with what you've done. This is a way, not necessarily the best way. So, but what I did was have and I'll talk about actually this keyword static today. But if you put static in there, it means that this variable is remembered from function invocation to function invocation. Whereas this variable, which doesn't have the static keyword, is set to false every time the function is called. Pressed, if we end the function and it's true, the next time we come into the function, it would still be true. Okay. So, but initially so pressed actually keeps track of the switch state, whether it's pressed or released. If it's pressed, then pressed would be true. If it's released, it would be false. Okay, so that's always the switch state. So, but I only return true if it was not pressed the previous time, and then this is detecting if it's currently pressed. Okay, because this would be 0 when it's pressed. There's a not there that says if this is true, which means it's currently pressed. Okay, because not 0 would be 1, so it's currently pressed. Then change the state and return true. Set the return value to true. The wait here is just to allow for switch debouncing. And then the other thing I look for, if it was the else statement would be if it is pressed, but then released, set the press to false. So this always returns false except under this one case where it was previously not pressed and then it currently is pressed. Okay. Then it returns true. At all other times, it's going to return false. You say hope that's the way it works. That's the way it's supposed to work. It appears to work, okay, in the tests that I've done. And it's not the only way to do this, a number of different ways to do this, but this would be one way to check to see, to detect when that switch is first pressed. Because these push buttons are a little different. They're not like, normal toggle switches where you hold the state, right? So sometimes you can use push buttons in a number of different ways. You may want to return true every time it's pressed, okay? Or return true only when it's released. Okay, there's times you want to do that. So you get the action that you want from the switch in software. You don't have the capability of modifying the hardware here. So any questions about this? Any questions about the project that's due tomorrow? Some of you have already turned it in. I hope more than a couple of you, but. Okay, actually, so in this next chapter, it's actually just a chapter on variables, but it gets into some of the details about, like in particular, that static keyword, and more specifically about where variables are stored in memory, and how we can actually, how the stack is used in a function call. But variables can be classified according to their scope and lifetime. Now, I think this is something that you should have seen back in your first programming class and discussion of this, and now looking back, maybe you can understand it a little better. Scope is the region of code over which the variable is accessible. So some variables only have function scope. So you can only access the variable from inside that function. Some variables actually have global scope. They can be accessed from any function. C actually even allows you to have defined variables which only have file scope. They can be accessed by any function that's within that same source code file. Okay. Lifetime, variables also have lifetime. They'll typically be temporary, or maybe only exist while the function is called. Okay. Or they may be permanent, okay, or have program lifetime. They'll exist from the time the program is started until the time the program completes. So we'll start the discussion, and we'll get into a discussion of the stack today. I want to start by talking about local versus global. So local variables are defined inside functions. C actually allows you to create local variables just inside blocks. You can throw a pair of curly braces in anywhere inside a function, and you can define additional variables inside the braces, and they only live inside the braces. But I'm not going to talk about that or say any more about it than I just did. And have function, sometimes called local scope. So what I want to do is talk about this using a series of short programs. So here's the first one, void foo1. We define A inside the function. A is local to the function. Can't call it from outside the function. Not by name anyway. Can't call it outside the function, and you shouldn't call it by pointer either because it actually lives on the stack. But every time you call this function, A would be initialized to 10. So this function would print 10 every time you call it. Now, if you had another function, that tried to you get an error. A doesn't exist in this function. You get a compile time error. It would say unknown variable or undefined variable or something like that. Now, if we could have a third function where we have a variable A, it's a completely different A from in the foo1 function. Perfectly fine. You can imagine the reason why we would want this behavior. You know, in large projects, you know, with hundreds of files, hundreds of different functions written by different programmers, you know, everyone wants to use the variable A or I or something, especially for loop counters. So you wouldn't want just one instance of the variable to exist in all your program code. So A in this case has function scope or local scope. We can reuse it in other functions, but it's a completely different variable. We'll say a lot more about this a little later today. I'll talk about where A actually lives at the assembly language level. It lives on the stack. Now, these are non-static local variables, what I've defined so far. They also have function or temporary lifetime. Okay, so function scope and function lifetime. What that means that A really only exists when I call foo1. We'll see how that's done at the assembly language level. But when foo1 returns, A really doesn't exist in memory anymore. Okay, the memory is allocated for A while the function is running, and then that is released when the function returns. So that's what's meant by temporary lifetime. It really only exists. It's initialized, in this case, to 10 when the function is called. It's actually allocated on the stack, initialized, can be used within the function. When we return from the function, that space is freed on the stack. It really no longer exists. So with regard to lifetime, here's a simple example. Kind of perhaps illustrating this. And here I'm incrementing A after it's actually passed to the printf function, so it's A++ here. But this will print 0 every time. Every time we call it, this is going to print 0. Okay, print 0 once. When we call it again, it will print 0. The A++ here does nothing. Plus. It increments it. If I had another printf after that, then it would print 1 because it increments it locally. But every time I call this function, A gets reinitialized to 0. Now we can change that behavior. Static local variables have program It's often called permanent, but it doesn't really live forever. It just lives from the time you start the program until the program exits, okay? And then it's freed. But static local variables have permanent lifetime. They're created and initialized when the program is started and exist until the program ends. So here's how I make a static local variable. Just add the keyword static. But now this lives in a completely different area of memory. No longer lives on the stack. It lives in a, when we start the program, space on the space in memory is allocated for A, and that space is reserved for that variable for the entire duration of the program. So now if I did this, the first time I call it, it would print 0, because here it's the post increment. If I had the pluses on the left-hand side, it would pre-increment, it would print 1 the first time. But it prints 0 the first time it's called, then 1, then 2, then 3. This little keyword here, static, makes a huge difference about where the variable is actually stored. Okay, sometimes you want this behavior. You want to remember state. That's like in that switch example. Every time I call that function, I want to remember what the previous state of the switch is. Okay. Or, if we want some little counter object, I want to counter, I can put, I can put the counter in a function so that every time I call the function, it increments the counter by 1, and then maybe returns the value of the counter. So sometimes we want this behavior. Most of the time, I think probably 99% of the time you're writing programs that you don't want that behavior, right? You want your variables to actually be local and then, or have temporary scope and then disappear when you write the function. So use of this is not common, but sometimes you need it if you need to remember state. Okay. Any questions about that? I'll talk a little bit more about where this guy lives. This guy does not live on the stack. Okay, and space is allocated in memory when the program is loaded into memory. Non-static global variables are defined outside of functions and have program or permanent lifetime and a global scope. So the local versus global really applies to their visibility. So even this static A, I can't access from outside the function. Okay, the compiler prevents that. I can't refer to this variable by name outside of this function. So it has local scope. It's really not visible outside the function. Global variables, on the other hand, are visible outside of the function. And here I'm going to have, actually, my example, I'm going to have 2 different files. And here I'll define A outside of any function. Now I could increment this A from inside the function. The A variable here references the global A. All the functions in this file that reference A would reference this global variable. It has permanent lifetime as well. So once it's incremented, you know, I call it again, it would continue to increment. So the first time I call bar 1, it would be incremented to 1, then 2, then 3. Now, and here's where it gets a little weird. I could have, if I had an int A in this function, a variable with the exact same name as the global function, it's really a new A that has local scope and wouldn't affect this one. Okay, so that's where things get a little tricky, right? You probably want to use fairly unique names for your global variables. But again, sometimes if I know in bar 1 I don't really want to use this A, I'm free to define another A. But if I want to use it, now why would you want to do something like this? It's usually because you need to pass a value maybe between functions or share it between functions or different files. A better procedure is probably maybe to pass the variable by function call, but that's not always possible. Now, here in file 2, and the extern keyword here says, I'm trying to access a global variable that's defined somewhere else in some other file. But when I do that, this would be a function now that would decrement that same value. And, you know, back in the same file, I could have another function that prints the value. I don't need to declare A again, and I shouldn't, because if I did, I would get a local variable A when I want to access this global variable. Now, here A is non-static, but static global variables have program permanent lifetime but only file scope. So static is kind of being used completely differently here than when it's applied to local variables. Local variables always have function scope. When I apply the static keyword to it, it gets a permanent lifetime. Global variables always have a permanent lifetime. When I apply the static keyword to a global variable, it actually changes the scope. Okay, so in one case, it changes the lifetime when it's inside a function. In another case, it actually changes the visibility of the variable. So here again, I have to use two files that kind of illustrate the difference. So if I put the static keyword in front of the definition here, this limits the visibility. It says only functions in this file can see this variable. So it allows you to collect functions together that maybe have a common purpose. This would refer to that same variable as would this. %B of A be the same A, but in a different file. String int A. This would be an error. I can't access A if it's got the static keyword in it from another file. Okay, the compiler enforces that. So if I tried to decrement A here, it wouldn't work because it doesn't have global visibility. So how does the compiler pull this off? Really, it's only non-static local variables that are kind of different. Those are the only ones that have the temporary lifetime. Those are the only ones that are actually allocated on the stack. The static locals and then the globals all have permanent lifetime and are allocated in memory when the program is started, and then actually not freed until your program finishes. And so they would have a kind of a permanent address. The duration of the program. But let's talk about the stack. And we've talked about it previously, how you can use it to save values. I mean, you've only got a limited number of registers in this particular microcontroller, what, 14 different registers or something, right? And then there's a procedure when we're using functions, you can use registers 1 through 4 without having to save them. But any other registers should be saved on the stack and then restored to their state when your function ends. So when you call a function, it creates what's known as a stack frame. When a function is called. And on the stack frame, there can be input parameters. And you remember the convention with the ARM is that the first parameter is actually stored in register R0. So it should be stored in register R0, and then we branch to the function. Or if there's two parameters, we put them into R0 and R1 and then call the function. Up to 4 parameters, we put them in R0, R1, R2, R3, and then call the function. And then the function would expect the first 4 input parameters to be in those first 4 registers. Well, C actually allows for an arbitrary number of parameters. We don't have an infinite number of registers, though. Okay, so there has to be some limit. In ARM, the convention is 4 input parameters are passed by in registers. Any more than that, they're actually pushed on the stack. So if you have a 5th parameter or a 6th parameter, those are all pushed on the stack. The reason for that, it's a trade-off between, efficiency and program ease, I guess you'd say. C allows you to pass any number of parameters to a function. We could pass them all on the stack. Okay? Then you're only limited by how much stack memory you have. But that's inefficient. Okay? It's faster to actually put them in a register. If they're on the stack, we have to go retrieve them from the stack. So that's an additional move operation. if your functions, if you have functions that never have more than 4 parameters, you're never going to have to push and pull parameters from the stack. Okay, so it's more efficient. And the compiler takes care of all this for you. You don't really have to know that when you program at the C language level. But when you're writing assembly language functions, you have to know this. You have to know where the first input parameter is stored. Is it already in R0, or do I have to get it off the stack? And then the other thing that's pushed when we do, or what you should do is also push the return address onto the stack. Now this is necessary if we call then another function, then the return address is in the link register. And so if we call another function, that link register is overwritten. So we need to store that return address on the stack. Then if you recall the first thing that we did, way back when we were doing this assembly language programming, is we saved additional registers on the stack. You know, if you modified R5 or R4 or R10, you need to save those values on the stack, because the function that calls you assumes that those values are going to be there when the function returns. So again, you're free to mess around. If you can write your assembly language program and only use registers R0 through R3, then you don't need to save anything onto the stack. But if you move something else into R6, you need to make sure that you store the R6 value onto the stack, because that's the only place you've got to store, right? Unless you allocate it on the heap, but then it's a lot easier to store on the stack. It's just a simple push. And then the other thing, and this is what we haven't talked about, is space for local variables is allocated on the stack as well. Now, the local variables are at the top of the stack. But if you remember the way this stack works in our processor, it decrements with every push. So that would be at the lowest address. Now it gets a little confusing. It'll be confusing with what I put on the board and also in the textbook, because you think of a stack as like a stack of dishes or a stack of computers or something like that, and putting things on the top, right? So usually that's how we'll draw it, but that means that the lowest address is actually at the highest vertical location. So it can be a little confusing. So, and we'll get into some detail on this, but after the frame is created, the stack pointer is copied to a register that is used as the stack frame pointer. Okay. So, and we'll see this. So after, we'll allocate space for the local variables, and then we'll copy the current value of the stack pointer into another register, and then access our local variables as offsets relative to that register, relative to the stack frame pointer. Because as we push and pull other things, push and pop other things onto the stack pointer value changes. So the offset to our local variables would change. So, I mean, you could still handle that in your program code, but it gets pretty messy. This way, your offsets are always constant. So what I want to try and show is a fragment of a C language program, the corresponding assembly language, and then what's going on with the stack. And I'm going to keep it really pretty simple. This function doesn't even take any input parameters. But I've got two non-static local variables. So these would be on the stack. And then I've got a 10 element int array, which would also be allocated on the stack. So if you're working with a processor that has a limited stack size, you want to be careful making large arrays, allocating large arrays like this. You know, a simple trick is to declare them to be static, and then they would be actually stored somewhere else instead of on the stack. It's usually not an issue when you're programming on the PC, because I think of the PC, it sets aside like 2 gigabytes of heap and 2 gigabytes of virtual stack space. You got all kinds of memory on your modern PC, but that's not true with microcontrollers. And then sum equals 0, and then array 0 equals 0. So what's the equivalent assembly language look like? Well, the first thing that we do in our foo function and assembly, and this is what the compiler does. Okay? The compiler would translate the C into the assembly language. So the assembly language is going to look something like this. I'll put some instructions down here. And then some comments. Okay. And I'll make notes over here about the comments. So comment 1. We're going to save any registers that we use in our assembly language program. Okay. Now, so this implies I'm going to use registers R4 and R5. I'm actually going to use R11 as the stack frame pointer. That's what our compiler uses by convention. Okay, you could use any one of them. And then the link register contains my return address. Okay. The address of the function that called foo. Okay, so I've got to get back there at the end of my function. So now I want to save that, because if I call another function, the link register would be overwritten automatically with the return address to this function. And then the next thing that's done in creating our stack frame is we decrement our stack pointer by 48 bytes. So this is allocating space for our non-static locals. Let me try and draw a picture of what's going on with the stack at this point. Now the push, when you feed it a register list, so you can look in the back of the textbook for this. It pushes the registers. It'll first push the highest register number. The link register is actually R14, so it would be pushed on the stack first. So our stack would first contain our link register, and then what else have I pushed? R11. R5, these are all 32-bit words, R4. And then remember, we decrement before our push. So at this point, the stack pointer would be pointing right here at R4. Okay. This is our current stack pointer, after step 1. And then the next statement is copy the stack pointer, R11. So note 2 and note 3. So at step 2, I've allocated space for all of my locals. Array 9, and then array 0. And my stack pointer is pointing right here after I subtracted 48 from it. And then at step 3, R11 is pointing right here also. I copied that over. Right. So these are actually lower addresses. This is where you have to be careful when you're working with stacks, right? The stack pointer decrements. Normally, when we're talking about memory, I show 1000, 1001, 1002, 1003. But here the addresses are actually getting smaller as we're going up the board because it looks like a stack of objects. Okay? But that can be really confusing, where I'm really now drawing memory kind of upside down. And then so 3R11 is the stack frame pointer. So this would be actually R11 plus 0. This would be R11. This would be R11 plus how many do I have on there? 48. This would be R11 plus 48. This would be plus 44. This would be plus 40, because each of these are 4 bytes. This is R11 plus 0, or where R11 is pointing. Then now for the rest of my function, I won't change R11 at all. My stack pointer can change as I push and pop things on the stack. But now to do the next 2 lines in C, I would clear R0, for example, and then store R0 at this memory location. So to clear sum, it was 44, an offset of 44. And the compiler would keep track of this, the offset of where sum is. Every time I use sum now in my C program, it's referring to this 44-byte offset from R11. And then similarly to clear the first element of the array, it's at offset 0. The second element would be at offset 4. And so on and so forth. Now I'll just make up something here. Okay, because I'm returning an int. So what's at the bottom here? Well, to be consistent here, I'll move into R0 the value 10. Because remember, my return variable is in register R0. And then the other thing I do at this point is Now, if I've had pushes and pops off the stack, there has to be an equal number. Okay. I want to restore the stack pointer back to where it was when I was called. Okay. So there may be pushes and pops in here, but when I get down to the end, I know I want to restore my stack pointer, so I'm going to add to the stack pointer this 48, this offset of 48, which is essentially deallocating all of my local variables off the stack. Because now if I call another function, stack pointer hasn't changed, these old values will be overwritten. The next time I call this function, the stack pointer could be pointing to somewhere else. Local variable space would be allocated for these same variables. Okay, they're really different because they're temporary. They're really created brand new every time I call the function. Could be created a different place on the stack. And then the last thing I need to do is pop R4, R5, R11, and then you'll see this will actually restore the link register back to the program counter, so that the next instruction, that's my return address, the next instruction is back in the calling function. Okay, so 4, 5, 6, 7, and 8. So what's going on here? So with 4, I'm accessing locals, non-static locals, through offsets from the stack frame pointer, which is R11 here. So it's really 4 and 5. One is accessing sum, the other is accessing array. The first element of the array, then would be R11, 4 would be the second element of the array. If we were doing some sort of loop, that loop variable would typically be in another register, and it'd be R11, that register value for the offset. And 6, return value is in R0. That's because I'm returning, here in my function definition, I'm returning an int. If it were a void function, I wouldn't need to put anything in R0. 7 is restore the stack pointer, and then 8 is restore registers, and actually by copying the link register, the return address into the program counter, I'm automatically returning with that one pop instruction. Now, other topics we'll discuss in this chapter. We'll talk a little bit about parameter passing in more detail next time, but we also get into a topic that we haven't talked about. It's actually how floating point numbers are stored in microcontroller as well. So there's a standard representation for floating point numbers in memory, and so we'll get into a discussion of that. There's a completely separate floating point processor that's present in these ARM processors that uses its own set of assembly language instructions. Okay, we're not going to look at that in detail, but just get an overview of how that actually works. Any questions about any of this? I should mention, other than the non-static locals, All other variables would be at some particular address in memory, and that address would be the same throughout the entirety of the program. So they would be, when we access these other variables, we can load their address and then read and write the variable using that address. And that address would be fixed throughout the lifetime of the program. Only the non-static locals that are on the stack like this. All right. Count up to be updated.